Thamizhazhagan from University of Waterloo, and he's going to talk about on the structure of invertible elements in Fourier-Stieltjes algebra. Please go ahead, Aasaimani.
Thank you, Sandhya. I would like to thank the organizing committee for providing me this wonderful opportunity. And also I would like to register my thanks to my supervisors, Dr. Nico Sprong and Dr. Brian Forrest. This talk concerns about the structure of invertible elements in Fourier-Stieltjes algebra. Before getting to know what these Fourier-Stieltjes algebras are, let's recall what is an abstract index group of a Banach algebra. If we consider a commutative Banach algebra with identity, and if we collect all the invertible elements and give the norm topology, it becomes a topological group with exponential as an open subgroup. These exponentials is exactly the connected component of the identity. If we quotient out these exponential from the set of all invertible elements, what we get is abstract index group, and we denote it by H1 of A. The notation comes from the study of cohomology. If we consider any Banach algebra homomorphism between two Banach algebras A and B, then the homomorphism maps set of all invertible elements of A into set of all invertible elements of B, and it maps exponential into exponential. So this map induces a map at the level of index group. A very deep theorem about this is Arens-Royden theorem, which states that if you have a commutative Banach algebra with identity and spectrum delta A, then the the map induced by the Gelfand transform on the level of index group is an isomorphism. Okay, we'll come back to this consequence of this theorem a little later. This concerns the talk concerns about saying something reasonable about the index group of this Fourier-Stieltjes algebra. A little bit history, like around 65 to 72, Joseph Taylor was mainly invested in studying the structure of commutative convolution measure algebras. The definition is irrelevant, but think of these algebra as a measure algebra of a locally compact abelian group or a locally compact abelian topological semigroup. He used certain semigroup techniques and serious cohomological calculation on its maximal ideal space to provide very general factorization theorem. In fact, he produced two factorization theorem, and one is well-known Cohen's idempotent theorem, and other one is about the set of all invertible elements. So if we take any invertible element in this math frac A, there are distinct maximal group algebras. Maximal here, by the group algebra, we mean that it is isomorphic to some L1 of locally compact abelian group, and maximal means if you have any intersection with any other group algebra, a non-empty intersection, it has to be contained inside these group algebras. So the idea is, if you have any invertible element in this math frac A, then there exist elements nu i's from the unitized group algebras, and these are invertible in the unitized group algebra, and we can represent this measure as a convolution product of nu1 to nu(n) with an exponential. So this essentially says that the index group of this math frac A is exactly the direct sum of index group of certain maximal group algebras. The spectrum of the measure algebra is quite complicated, but the spectrum of these, the Gelfand spectrum of the group algebra is it's a dual group itself. So it's tractable in a sense that each of these, he is able to describe these invertible elements in terms of more approachable guys. For example, if we take a locally compact abelian group, and if the math frac is measure algebra, then each of these maximal group algebras are L1 of G tau, where G tau is G as a group, but its topology is finer than that of the group topology. When G is real line, there are only two topologies that is possible. One is the usual topology, the ambient group topology, and other one is a discrete topology. Okay. There are certain non-commutative analogues proposed for this L1 and L1G and the measure algebra M of G. In 1964, Imad introduced for any arbitrary locally compact group certain algebras, namely B of G. This is called the Fourier-Sturgis algebra. It's a collection of all the coefficient functions of continuous unitary representation. And A of G is Fourier algebra. It's nothing but the collection of coefficient functions of the left regular representation. Left regular representation is one of the important representation for any arbitrary locally compact group. And by the way, L1G is an ideal inside M of G. A of G is also an ideal inside B of G. A of G is Fourier algebra and B of G is Fourier-Sturgis algebra. And B0G is called Rachman algebra, which contains the B of G, those functions in B of G which vanish at infinity. Okay, the there are several developments made since 64 to ensure that these guys determines G. If B of G1 is isometrically isomorphic to B of G2, if G1 and G2 are topologically isomorphic, and so for A of G and so for B0 of G. And Bochner's theorem says exactly why these are the wonderful candidates for the analogous wonderful candidates in the non-commutative setup for L1G and M of G. When G is abelian with dual group G hat, the Fourier-Sturgis transform, and Fourier-Sturgis transform is nothing but the Gelfand transform of M of G restricted to the G, and Fourier transform is nothing but the Gelfand transform of L1G. And Fourier-Sturgis transform maps M of G isometrically onto B of G hat and L1G onto A of G hat. So in sense, these guys are the dual objects. The philosophy is that B of G corresponds to M of G hat and A of G corresponds to L1 of G hat. So the properties of M of G would correspond to B of G, and the properties of L1 of G would correspond to Fourier algebra A of G. So in that angle, so when we try to ask this factorization for general Fourier-Sturgis algebra, certain developments were made based on a spectral approach and also based on topological approach. Spectral approach is quite complicated to present in a 10-minute talk, but the topological approach is by my supervisor Nico Spronk and Monica Ellie. In 2007, Spronk and Monica Ellie developed the non-commutative dual analog of the spine of the abelian measure algebra. By spine is exactly, if we consider these maximal group algebras, we can take the closed linear span of these maximal group algebra. Taylor called this closed linear span as a spine of the maximal spine of the abelian measure algebra. So they developed the non-commutative dual analog, the spine of the measure algebra, and the conjecture. If you take is every invertible element U in B of G is of the form, if we can factorize them into V1 till Vn, so that Vi's are in a tractable object, and tractable objects are this Fourier algebras. So the Vi's belong to unitized Fourier algebra and they are invertible in it. But because of the duality, this topology now becomes a coarser topology, coarser than the ambient topology. For the case in M of G, we had finer than the ambient group topology. Okay. So let's get back to Arens-Royden theorem. And what does Arens-Royden theorem says is that the induced map by the Gelfand transform at the level of index groups is an isomorphism. There's a fairly decently easy corollary that can be said about this is if you have two Banach subalgebras such that the spectrum are the same, we can consider radicalizer algebra of A in B, their spectrums would be the same. Okay. Banach subalgebra such that the spectrum is same as the bigger algebra, then all the invertible elements in B can be expressed as invertible element of A times some exponential. Okay. So in general, this B0G, which is called Rachman algebra, is far bigger than A of G. But there are some cases where B0 of G becomes A of G. And those when it B0 of G becomes A of G, then we call it a regular. It happens only when B0G is a regular Banach algebra. So when you have regular Rachman algebras, then so the spectrum of B0 of G is exactly same as the spectrum of A of G, and the spectrum of A of G is nothing but the group G itself. Then we can express the invertible elements in B0G as exponential in B0 of G times A of times invertible elements in A of G. A fairly easier example comes from the Euclidean motion group, and any decomposition of the Fourier-Selges algebra is intimately related to how the representation decomposes. So the B of G can be decomposed in such a way that it's B0 of G plus the all the decompositions are L1 direct sum, and it can be decomposed in such a way that it's B0 of G plus Fourier algebra of the compact group SON. And the spectrum is the same, and the spectrum of B0G is same as spectrum of A of G, which is G, and the spectrum of B of G is union of two groups. And SON here is also the something called as a Bohr compactification of this group. So when this, and there is a reasonable, another remark that follows is whenever we have such decomposition where one is ideal, where A is equal to I plus B and I is an ideal and B is a closed subalgebra, we can easily, with a simple calculation, we can represent the invertible elements in A through the items in I and B. So this follows automatically. So from this example gave a structure to where to look at, what kind of example to look at. So we developed certain examples later. We collected several literatures that said examples. The first example, you can think of this as a compact group acting on the vector group such that the action has a non-trivial fixed points. The action at the levels of Lie groups has a non-trivial fixed points. And there are something called as totally minimal groups. These groups are such that the minimal group is such that there is no Hausdorff topology on the group coarser than that of the group topology. And totally minimal means if you consider any factor group, if you consider any factor group that is the quotient ordered by the closed normal subgroup, even that is minimal. Okay, so these have a structure theory that they always look like semi-direct product of a simply connected.
Sorry to interrupt, Mani. I think the talk was for 10 minutes. So maybe you would like to wrap it up a little bit faster. So
there are several examples that evolved looking at this structure, and this structure looks like B of G can be represented as the decomposition of these algebras. AR means that the radicalizer of the Fourier algebras, and each of these have an ideal structure, and the spectrum splits as the semilattice of these groups. And these groups can be determined by some central idempotence inside the spectrum. And the theorem is that the index group of B of G can be described exactly as the direct sum of index group of the Fourier algebra of these smaller groups. So hence we have desired factorization. And A of AX plus B, the group AX plus B with Taylor's analysis can also have a desired invertible element characterization. Thank you.
That was quite a challenge for giving a 10-minute talk. So thank you for that.